Okay, this video is about section 8.1, which is where we learn how to calculate the length of an arc. Not necessarily a circular arc, but just any arc that is part of any function. And so the strategy here is a lot like what we've done in the past for areas and volumes, which starts off by just looking at a way to approximate the area under a curve or the volume of a solid by chunking it into small chunks that are easy to calculate. So for example, with arc length, if we wanted to know the length of this arc, or say the length of any other curve, the simplest way to do it would just be to go from one endpoint to the other endpoint like this, draw like a dotted line there, and use the regular distance formula that you learned in geometry to find the distance between the 2 points, which looked like this. Okay, basically it comes from the Pythagorean theorem. That would be a really bad approximation, kind of like, finding the area under a curve using one big rectangle is usually not a very good approximation. So if we want to get a better approximation, we could maybe split that into 2 segments like this. So we could calculate that distance between those 2 points and then the distance between these 2 points. And if we added that segment's length and that segment's length together, we would get a slightly better approximation for the length of the arc. If we wanted to get a better approximation, you guys have kind of seen this before, we just need to use more pieces, more segments. Okay, just like when we're doing area under a curve, the more rectangles you use, the better the approximation for your area is. So if we were to split it up into 4, I'd have this segment's length, that segment's length, that segment's length, and that segment's length. Okay, and those lengths would be, again, better, still not exact, but better. So you can kind of tell where this is going. If we want this to be an exact length of the arc, we need to use an infinite number of segments. So instead of having one distance formula calculation, we would end up having a summation of a bunch of them, n of them, okay, and that would give us the bigger n gets, the better the approximation. So if we wanted an exact arc length, we would then have to do a limit as the number of arcs is approaching infinity. So my notation isn't really quite perfect here because I'm using geometry notation in combination with my calculus notation, but the bottom line is that this infinite limit of a summation, that is an integral, right? Elongated s for integral. So this distance formula, if we end up kind of rewriting that a little bit, we can call it delta x squared delta y squared, and I won't go through all the steps, but basically if you can get everything to be written in terms of x's and do a little factoring and some simplifying, it eventually turns into this square root of 1 plus f prime squared delta x, or dx on the end. Okay, so let me flip the page here. So the textbook way of writing this formula is right here. Okay, so this is how you calculate the length of any given arc based off of knowing its function. So you just find the function that you want to know the length of, the arc length of, find its derivative, and then you plug it into this integral formula. Okay, so example, say we had a function that looked like this, x to the 5th over 6 1 over 10x cubed, and we wanted to know the arc length between, just we'll go a little short distance here between 1 and 2. So first thing I need to do is find the derivative of this so that I know what to plug in for f prime. Okay, so that would be like having x to the 4th. I would need to bring down the 5, so that's going to change to 5/6 as my coefficient times x to the 4th. And then my second term here, this would be the same thing as having 1/10 times x to the -3rd, if I want to rewrite that as a power instead of a fraction. And so when I do the derivative of that, we will get -3/10 x to the -4th. Okay, so I'm going to take this. This is now my the derivative of the function I want to know the arc length of. So I just simply plug that into my arc length formula, and that would look like this. I go 1 to 2 because that's where my starting and ending points are in this case, and square root of 1 plus, and then my whole derivative squared. Okay, so I just typed that in my calculator and it tells me what my arc length is. If you want to check yourself to see if you're able to type that in correctly, you should be getting 5.254. Okay, one more quick example here if you need it. If not, you can feel free to stop it and start your homework. But if we had a function like this, and we wanted to know its arc length from, let's say, 0 to 2 on that closed interval, okay, then we would need to find the derivative of our function. Okay, that's the same thing as having 4 minus x squared to the 1/2 power. Might be easier to, again, differentiate when it's written as a power. So chain rule is in effect here. Okay, so I'm going to bring down the 1/2 power, subtract 1 from it, leave the inner function there, and then multiply by the inner function's derivative. So that would be -2x. I could combine some light terms here so it's easier to type into my formula. If I put my coefficients together, that would just be -1. So I'd have -x 4 minus x squared to the -1/2. Alright, so again, we just put that in our arc length formula. It would go 0 to 2 in this case. Alright, then my root 1 plus my derivative squared. Okay, so that derivative I just found goes right in there. Need my -1/2. Okay, and again, if you want to check yourself on that one, you should be getting, actually that comes out to be pi. Okay, so work on your 8.1 homework. Be ready to turn that in Monday.